Assume we have a function sigma that doesn't have to be continuous but is piecewise smooth. Explain the weak solution of the following Dirichlet problem. Okay, so by now we're familiar with the Dirichlet problem, but now we're going to talk about the weak solution. Okay, so rewriting what we have up there, we have the divergence of sigma gradient of u being equal to 0. But if this is 0, then even if I multiply it to a function, any function should be 0. Furthermore, if I integrate it, it should still be 0, right? Okay. Now, what do? I'm going to apply Green's theorem. I'm going to assume that phi is in the Hilbert space. So that's why I can apply Green's theorem and say, and safely ignore the part evaluated on the boundary. Okay, so all of this is going to be equal to the integral of sigma, gradient of u, gradient of v. This is sigma. And this has to be true, sorry for writing v, should be phi. This has to be true for all phi inside our Hilbert space. Okay, so y is this part, the bottom equality, better than the top equality, or what we had before? Well, notice that the top has two derivatives, two Nobel signs, while the bottom only has one. And sometimes this is better. This is better because we can only define one derivative. Okay, so anyway, this is what the weak solution is. We're finding u that satisfies this equation on the bottom for all phi. All right, now let's move on to part B. So part B, well, notice that we have a 3 here and a 1 here. So maybe we can write our sigma as a piecewise function, right? So this is going to be 1 if x is in 0, 1. It's going to be 3 if x is in -1, 0. So now I can rewrite the problem as -1 to 1, which is our omega, times sigma u prime, and then v prime. Notice that this form looks very similar to what I wrote right here, right? And I keep writing v prime. Sorry about that. Write it as phi prime. And this is equal to 0. And the problem says that this is equal to 0 for all phi, where for all continuous phi, where it's 0 on the boundary. Now, this should mean that negative the second derivative of u being equal to 0, right? So if u was a multivariate function, then this would be true. But right now, we can interpret this as the second derivative of u being equal to 0. We're going to use this fact later on, in fact, very soon. So anyways, let's keep writing. Let's just not change color. This is what we have above. U prime phi prime plus 3, -1 to 0, u prime phi prime, by definition of sigma that we just defined. Okay, and now what do? Now we can use integration by parts, right? We can use integration by parts. This is going to be let's see. So I'm going to integrate phi prime, and it's going to be phi times u prime evaluated at 0, 1 minus phi prime u prime prime. All right. Now what do we say u prime prime was? We said it was 0 right here. We said it was 0. So this integral becomes irrelevant. Similarly, the second part, we have 3 times phi and then u prime from -1 to 0. Let me just write in the x here. Okay, what else do we know? We know that phi evaluated on the boundaries, -1 and 0. Sorry, -1 and 1 are going to be 0 because by definition, right? And so we can ignore this part, and sorry, these are the parts that we don't want to ignore. We can ignore this part and this part. And all we have left is going to be, so the first part gets ignored, and we have negative phi of 0, u prime of 0, plus 3 phi of 0, u prime of 0, right? And phi can be any function, so it doesn't have to be 0, and therefore we can cancel it. We're not dividing by 0 right now. Okay, so what does it mean that u prime of 0 is equal to 3 times of u prime of 0? Well, let's be more precise here. Let's be more precise. This part is on the right side of the interval, right? The positive side. So really this is coming from the right. And this part is from the left because we have our evaluation going from -1 to 0, right? Okay. So how should we draw this? We have the second derivative being equal to 0. We're also given boundary information. We have u of -1 is -3, u of 1 is 1. U of -1 is -3, u of 1 is 1. Furthermore, at 0, the derivatives are, the derivative information, we could also derive this, right? So how do we incorporate all this information together? First of all, second derivative being equal to 0 means u of x is going to be linear. So I guess it's easier to just draw, right? So what do we have? We have at -1, we have -3. At 1, we have 1. And we're supposed to draw like a linear function, right? Like maybe like a straight line. Isn't going to work, but anyway, a linear function. Piecewise linear probably, right? And the derivative from the left on this side at 0 is a third of the derivative on the right side. So maybe this works, right? Going from here to here, and then going from here to here. Notice that the slopes are 1 and 3, since we go 3 up. Right, so this piecewise linear function satisfies all the properties that we derived here. Okay. Remember what sigma was? Sigma. We said it was a piecewise linear. Let me actually copy paste this. Okay. sigma was a piecewise linear function, and it was 1 on the positives, and let's use a white line. Okay, 1 here, and then 3 here from -1 to 0 to 1. So this is 1, 2, 3. So what's going on here? Well, it looks like sigma is some sort of a density or whatever. So maybe we can think of it like this. In terms of physical terms, we can draw some water. And you know how when you put a straw in a water, we expect our straw to look like that, but to our naked eye, it looks something like that, right? Looks discontinuous. What is this? This is Snell's law from physics, right? So something like this is happening, and we are actually modeling a function that looks like this.